All right, those of you who might be watching right now, I'm just sending it out on Remind. So if you hear me typing, that's just me making sure people get the code to tune in, not turn in, tune in. All right, so we're doing Regents Review 2, which is Physical Behavior of Matter. So if you hear me typing away again, that's just me just sending out the code on Remind, not the code, the link to the video, whatever. Can't talk, that's okay. Only have to talk for the next hour. So if you're tuning in right now, usually how this goes, if you didn't watch yesterday's, is I don't really do practice problems. I just kind of review the concepts and everything involved in these 2 units as quickly without being overwhelming as I can. Chemistry is pretty dense. There's a lot of material to cover in chem. So I'm going to hit the major points as best as I can. Tonight is anything and everything having to do with heat and gases. So I'll be getting into the concepts involving these things. This is kind of part 2, going over the physical aspect, the physical changes involved in chemistry. And then we'll start getting into the chemical changes in chemistry for basically the rest of these review sessions. Except for the last unit, which is all nuclear chem, which are a bit different. They're still they're like weird chemical reactions, I'll consider them, but they're their own beast. So we're going to talk about heat, temperature. I'm just looking at my outline here. Talk about the temperature conversions, kinetic energy, potential energy, heating and cooling curves, Q, when to use any of the equations involving Q, which is heat. What else do we got? Let's see. Yep, Q, 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 Q. Lots of Q. Then we'll get into gases. Because we talked a little bit, maybe do a little bit of solids and liquids review, just to go over some terms. They're not too many. Then we'll get into gases, pressure, volume, and temperature, the graphs, the relationships, the equations involving those, and we'll call it a night. So we'll get started here. First thing I want to do is kind of review some terms that will be helpful, that we'll be talking about a lot as this review session goes along. We have kinetic energy, and I'm going to abbreviate energy, NRG. We have potential energy. Where kinetic energy is just the energy of motion. It's usually associated with temperature changes. So when we think kinetic energy, we think of changing temperatures. So when we look at those heating and cooling curves, any part of the heating and cooling curve that's changing temperature, we consider change in kinetic energy. We have potential energy, which is like stored energy. It's like defined as the energy of position. So it is all about phase changes, not temperature changes. So when we think of kinetic energy, we think of temperature. When we think of temperature changes, I should say, and we think of potential energy dealing with phases. Temperature itself is the same as average, and I'll capitalize that, kinetic energy. So there's a lot of questions year to year to year on which of these particles has the highest average kinetic energy. That's usually how they end up wording it. And it's just the particles that are at the highest temperature. So temperature is the same as average kinetic energy. So as temperature goes up, average kinetic energy therefore is also going up, and vice versa. It doesn't really depend on amount or size or anything like that. So they'll throw in other units to confuse you, like milliliters or grams. It doesn't matter. It's all about temperature here. So don't let that confuse you. Heat is a quantity of energy, but a lot of times you'll see that written in kind of terms using thermal energy. And this is one question where I've actually seen it repeated word for word the same. So when we think of thermal energy, we think of motion. The energy of motion / moving particles. And that exact wording, literally I've seen appear 2 Regents in a row in the same year, like in June and then in the following January or vice versa, something like that. So they like to throw in these words called thermal energy. And when we think thermal energy, we just want to think heat or Q. There was a question on the midterm that a lot of students missed because they thought thermal energy was the same thing as temperature, and it's not. Because thermal energy is dealing with heat. Heat and temperature are not the same. You can't measure heat directly, at least. Yes, as temperature goes up, that might give you a clue as to what's happening, but temperature is measured in like degrees, not a unit of energy. Heat is a unit of energy, so they're a bit different. So, let me see, was that, nope, nothing important. Okay, so temperature, we have a few different scales for temperature, but usually you're going to see Celsius or Kelvin, and there's a conversion for that on the reference table that I want to make sure we remember exists. So if you ever need to convert temperature from Celsius to Kelvin or vice versa, sometimes it's extremely direct in the question. Like it'll just say, hey, convert this temperature to Celsius, or hey, convert this temperature to Kelvin. Or if you're using this equation, the combined gas law, that temperature must be in Kelvin. The conversion's right here. Very simple. Kelvin equals Celsius plus 273. So if you want to get Celsius, you just subtract 273 from both sides and get Celsius equals Kelvin minus 273 instead of plus. So anytime you're given something to convert temperature-wise, go to the reference table. Don't try to memorize this if you don't want to. I mean, if you want to memorize it for speed, but you have 3 hours in June, which is plenty of time. And a lot of you will finish before the 3 hours is up. So if you ever need to convert temperature, it's there for you. Use it. What else can we start saying about heat? So thermal energy / heat. It's a transfer. It always transfers from hot to cold. And this is already a concept where if you've been keeping up with Castle Learnings, doing the Regents reviews we've been doing in class, this question also pops up often. So it always transfers from a hot object to a cold object. The cold object does not make you feel cold by giving you coldness. The cold object is taking away your heat. So it will always go from a high temp to a low temp. Kind of like diffusion. If you remember bio, diffusion of particles always went from a higher concentration of particles to a lower concentration of particles. Heat diffuses, we can think of it as, sometimes we can think of it as diffusion, as going from a high temperature to a low temperature. So that's just something to keep in mind. It does pop up fairly often, so don't forget about that. Let's see. What else? So we talked about phases of matter last night in that review. We did solids, liquids, and gases. We did particle diagrams of solids, liquids, and gases. So why not talk about heating curves? Because heating curves are involving a lot of phase changes. So heating curves look something like this, where the bottom is time, and this is usually temperature. And we'll say it's temperature in Kelvin. Not that that matters. And no matter what the substance is, the heating curve's principles are correct or stay true. So here we have solid, liquid, gas. And here we have the phase change, which we'll call vaporization. And here we have a phase change of melting, or melt. So, as you move up this graph here from left to right, you go from a solid, and then when it starts melting, when it hits that phase change right here, it exists as solid and liquid. You're not fully liquid yet, you're not yet no longer solid. You're in that mixture phase where it's that solid slowly turning into a liquid, which is the same thing here. Not V, G. When you get to the vaporization stage, right here, that is both a liquid and a gas at the same time. So not quite all that liquid is vaporized yet. Some of it's still a liquid. It's not quite fully a gas. So we're in that mixture of liquids and gases. And I'm actually going to make these different colors so I can kind of talk about it and make this a bit more accurate looking. So I'm going to make this one a bit shorter than the one up top. Then we're going to come up here. I'm going to make this one a bit longer. And then that top portion is still a gas. All right, so the red, any of the phases you see in red, solid, liquid, and gas, so any of these red parts is going to be an increase in kinetic energy, and potential energy stays the same. So it doesn't go up, it doesn't go down, it's staying the same. There's no change. And these green portions, where these phase changes are occurring, equals an increase in potential energy, while kinetic energy stays the same, remains constant. You're not changing the temperature. So anytime you hit those phase changes, the temperature is staying the same. So the kinetic energy is not going down, it is also staying the same. So anytime you're at this green part here, these are your phase changes in that diagram, which means temperature is constant. All right, so just tips involving heating curves generally speaking. Make sure if you're given a heating curve, especially in a short answer question, that you read the context of the question, read that little blurb at the top. Sometimes they'll give you like a partial heating curve. Well, they'll only give you like the bottom piece, like it'll just have this part I highlighted here just missing. It just won't be there, and it'll just give you that bottom piece. And you might assume incorrectly that you're starting down there as solid, and they might be just showing you the liquid and gas phases. And the same is true for cooling curves, which I'll draw in a minute. Make sure you read the context of the problem to see what phase they're starting you at. Don't just assume you start as a solid in a heating curve. Don't just assume you start as a gas in a cooling curve. Sometimes they'll purposely say, hey, this is a liquid at 200 degrees. And it'll just show you the liquid to freeze to solid portion of a cooling curve. So just make sure you're reading the context of the problem, and you should be okay. Watch my previous video on drawing particle diagrams, but they do like to take these heating curves and say, hey, draw a particle diagram for the two phases right here, solid and liquid. Or hey, draw the particle diagram for the phase that exists right there. And they might label these like A, B, C, D, E, and ask you to draw particle diagrams at B, particle diagrams at C, etc. If you want help on particle diagrams, which if you don't remember, if you didn't check out yesterday, are just those diagrams where you're drawing the circles representing particles, watch yesterday's video. That's Regents Review 1. I go into pretty in-depth length on how to draw a bunch of different particle diagrams in all different phases, etc. All right, cooling curve. Cooling curve is the same thing, but in reverse. So I'm not going to spend too much time on this. but I just want to highlight a few things. So we got gas, liquid, solid. Here it's condensing. So it exists as a gas and a liquid. And here it's freezing. Liquid and a solid. So it's the same thing as a heating curve, just kind of rotated a little bit. So now you're a gas at the high temperature and a solid at the low temperature. Same thing is true here. Anywhere the temperature is changing, so anywhere where you're a solid, liquid, or gas, anytime you see that, that means the temperature is changing, which means the kinetic energy is changing. The only difference is that in a cooling curve, the temperature is going down. So as the temperature goes down, the kinetic energy goes down. And here, since it's a cooling curve, when the temperature is constant, your potential energy is going down when your temperature is remaining constant. That's really the only difference. Since it's a cooling curve, everything is going down this time instead of up. So again, be on the lookout, same types of questions here. Draw a particle diagram for this phase, at this point, at this time, etc., etc. Let's go and review endo versus exothermic. So endothermic, usually what I highlighted in class, you have endo, enter, kind of sounds like heat's entering. Ooh, that's an M. Come on now. Anytime heat's entering, it's an endothermic reaction. So anytime you're going this direction from phase to phase, that's endothermic. So solid to liquid, solid sublimation, liquid to gas, any of these phases are endothermic phase changes. Exothermic, exiting, heat is leaving, heat leaves, heat exits, is the exact opposite of endothermic. So you start as a gas or a liquid and you're going down the cooling curve here. So as heat is leaving and leaving and leaving, the substance is getting cooler and cooler and cooler. It will start condensing from gas to liquid. It'll start freezing from liquid to solid, or it'll deposition from gas to solid immediately if you cool it extremely fast. That's endo and exothermic. Cool. All right. Now, I think this segues all of these heat terms, all these heat graphs, segue into those Q equations. So let's take a peek at the Q equations. How do we know when to use the Q equations? You're going to see something about heat. It's asking you about, or it mentions something about heat. You use the Q equation. Sometimes if we go to our table D here, joules, it'll say something about joules in the question. Joules is a unit used to measure energy, aka heat. Heat's a form of energy. So if you see joules in the problem, or it wants you to calculate joules, or it wants you to calculate how much heat was absorbed, how much heat was released, or it wants you to calculate anything about the final temperature when the heat of the reaction has changed in this manner, anything about heat and a unit that it wants. It wants you to solve a problem and get a number involving heat. You're using one of these Q equations. If temperature is involved, that's Q equals MC delta T, which I always say is MCAT. So you use the MCAT equation, this equation I've highlighted in yellow, when you're trying to solve a problem involving a temperature change and heat. AKA, you're on that heating curve and you're not at the phase change. So you're on a heating curve or a cooling curve, and you're not here, because that's where the temperature is not changing. You're being asked to calculate something involving a change in one of those circled regions on our heating curve. That's the equation you use. Usually, most questions I've seen have you calculate Q, that's like the number one, or something in delta H. where delta H is the change in temperature, aka the final temperature, which I'll abbreviate TF, minus the initial temperature, which I'll abbreviate TI. A lot of students forget where C is. C is the specific heat capacity, and it's almost never given to you in the problem. So you have to do a little bit of hunting in the reference table. Go to the constants for water, table B, which I would like to call your Q table. Anything involving one of the Q equations is from this table. And there's your specific heat capacity. So that's C in the Q equals MCAT equations. I just drew some parentheses around C. If you're asked to find Q, aka heat, and there's a temperature change involved, and you know you need to use Q equals MCAT, specific heat capacity is at the front of the reference table. Next, the other two Q equations. We have fusion and we have vaporization. And I'll highlight these in different colors. Not that it really matters. So the other two Q equations, Q equals MHF is when you have a melting occurring. And Q equals MHV is when you have some sort of boiling or vaporization occurring. So the substance is being vaporized, aka phase changes. So you use, if we think of a heating curve, this is where you use your HF equation when a substance is melting, because the temperature is not changing. Notice, temperature is not even a variable in this equation. And then we use the HV when a substance is undergoing vaporization. So, it's a much simpler equation. There's no deltas involved. All you need to know is where is HF and where is HV. Well, these are equations involving Q. So I'm going to go to my table that I've called my Q table. And we got HF here. And we have HV there. So anything involving heat, aka Q, look at the equation on table T. Look at the constants you may or may not need on table B, which I'm nicknaming table Q. So, one more thing to highlight involving these equations. Again, Q equals MCAT. Look for buzzwords involving heat. You see a temperature change, where it asks you directly to find the temperature change. Usually those are your big buzzwords. It asks you about heat. Maybe it'll mention the word joules, because joules is the unit of energy for heat. So this is the unit for Q. Something like that will cue you in that I need to use the MCAT equation. So I know temperature appears in multiple equations. It's in P1, V1, T1. But the key here is heat, not temperature, heat. Link for and look for heat. Once you've determined heat's in the problem, then wonder, okay, is it MCAT, HF, or HV? If there's a temperature change, it's MCAT. Sometimes I think when you're solving for, let's say that the question wants you to solve for the final temperature. So that's your variable. The thing I've highlighted in red is that can be a little bit of a pain in the butt to solve algebraically, and you might make a silly mistake. So what I usually encourage people to do is divide both sides by MC here, get Q over MC equals delta T. And you don't have to do this. If you want to set up your variable using TF, go for it. Get some answer for delta T, then it just becomes a little bit of simpler, I think, algebra. You'll have, let's say the answer here is 10. You know your delta T is 10. Well, you do 10 equals TF minus TI, where they've given you one of those. Usually they give you the initial temperature. And then all you have to do is add TI to both sides to get your final answer. I put a couple problems like that in the practice problems for this unit, for this review session, I guess I should say. So just be on the lookout for those when you're working on these. They're not going to be on my website tonight, because the video won't be on my website tonight, but they will be on my website tomorrow morning, if the video works properly. And that's what I say about those equations. So I think I'm going to go ahead and move on to gases. I don't know if I want to talk about solids and liquids tonight. It's not much to say. There's a little bit of table H involved with solids and liquids, but I like to talk about table H when I talk about intermolecular forces. So I might keep it away for now. I will mention entropy now, though, before we move on to gases. Entropy, same thing as disorder. Usually we just use the word chaos because it's easier to say, but really it's about, and how the wording you'll see in the Regents and the wording a lot of chemistry teachers use is disorder. Entropy measures disorder. So a solid versus a liquid versus a gas, entropy is increasing this way. So entropy increases as you change phase from a solid to liquid to gas. Also, when we think of entropy, don't say like closer together. So don't say a solid particles are closer. We don't like that. We don't like to hear that. Because it's not that they're closer together. A solid particles are more ordered. Or they're less disordered. That's really a better answer. Because we talked about water last night. Water's particles as a solid are further apart than water's particles as a liquid. Because water's a little weird. Last year, this was a question, and we got this answer a lot. Where they said, why does, they were comparing, let's say, I forget what they're comparing, but it doesn't matter. H2O as a solid versus H2O as a liquid. And you had to, the question was about why does the H2O as a solid have less entropy or something like that. Where the question was involving entropy. And a lot of students said, oh, the solid particles are closer together. That's not true for water. What we want to say, what is true for all substances, when we want to say the solid particles are more ordered. And that kind of segues now into gases, because gases have a large entropy. So that's basically it for heat. I think that's a good place to call it there. Let's talk about gases. Let's talk about ideal gases. And I'm going to do this in class as well, because this is big. This is big. So ideal gas has these assumptions involved in the molecular theory. It's not verbiage we use too often. We haven't talked about this in a very long time. But there was assumptions involving this. So, when you're at a high temp and a low pressure, you have an ideal gas. The higher the temperature, the lower the pressure, the more ideal your gas becomes. The more your gases in the real world start behaving like this model for gases. As you really crank up the temperature and really lower the pressure, they're going to start behaving as follows. 1, pretty much no volume. That at least when I talk about the particles. The particles essentially no space. They're so darn tiny. We just say, they don't have volume. 2, no attraction. Hey, hey.
Hey, hey.
Can you give me a seltzer from the fridge?
Sure.
Thanks. All right, got my tie-dye shirt. Looking good. All right. So they have no volume. There's no attraction. So the particles don't attract each other, aka no IMFs. But let's hold on IMFs for now. Thank you. So no attraction, no volume. 3. They're moving constantly and randomly. So, high temp, low pressure, we got no volume, no attraction for each other. They're constantly moving randomly. They collide, what we say, elastically. Elastically. I think that's just spelled elastically. Which means they 100% transfer energy when they collide with each other. Or when they collide with the walls. So when they collide with each other, or they hit the walls of the container. Yeah. So this is for ideal gases, not real gases. So no volume, no attraction for each other. They're moving randomly. They're moving constantly. They collide elastically. And this is kind of a subset of 2, but since they don't attract each other, straight lines. So that's the last bit. They always move in straight lines. They don't curve when they're at a high temperature, low pressure like this. All right. So this was question 14 on the June 2015 Regents that we've done in class today in my 2nd and 4th blocks. And I guess we did that in 3rd block a while ago. It really depends on where you are or if you've been in class. So that was, I said I didn't really want to go over 14 yet because I'm going to go over it later. There's 14. All right. Next, Avogadro's law. Avocado's law? No. Avogadro's law. So, at same temp / pressure, at same temperature and pressure, which will usually in problems, I'll just say STP, which doesn't stand for same temperature and pressure. It stands for standard temperature and pressure, but they'll usually just say at STP. So at same temperature and pressure, same volume equals same number of particles. So, for example, if you're at STP, 5 liters of CO2 will have the same particles as 5 liters of argon, which will have the same amount of particles as 5 liters of helium. So these all have the same particles. And this is gases only. So this rule only applies to gases. And this question pops up like constantly. So usually they'll word it as like 2 liters of carbon dioxide has the same amount of molecules as what? And the answer is 2 liters of whatever gas that they give you. So these are all gases, so this is true for gases only. Because all gases will take up the volume of a container. So the analogy I usually give, I mean, it's not the best, but if you go to the grocery store, a 2-liter bottle of Pepsi has the same amount of stuff in it as a 2-liter bottle of Mountain Dew, which is the same amount of stuff in it as a 2-liter bottle of Coke. So it doesn't matter what the soda is, if their volumes are the same, they have the same amount of stuff in them. So for gases, if their volumes are the same, they have the same amount of particles in them. It's just a rule. Let's see. So that's Avogadro's law. I almost said avocados. Let's talk about P1, V1, T1. Okay, so P1, V1, T1. The equation on the reference table. So if you go to your reference table, you find the combined gas law. We already talked about this a little bit. It's got to be in Kelvin. Your temperature needs to be in Kelvin. If it's not, convert it to Kelvin. The end. So this equation all involves change. So all of these variables in this equation are going to be changing in some way, not being constant. They'll give you a bunch of information, and it'll say this, and it's at a volume of that, and temperature of this. What's the new volume if the pressure is increased to blank and the temperature is decreased to blank? Or they might keep one of the units constant. So they'll say at a constant temperature, or they'll say at 200 degrees, and if something stays constant, if the temperature stays constant, you can cross it out and just do P1V1 equals P2V2. Or if the volume stays constant, you can cross it out and just do P1 over T1 equals P2 over T2. Either way, you're using the P1V1 T1 equation when there's some sort of happening between pressure, volume, and temperature. So it's going to have a change. All right? Honors kiddos, if you're watching this, don't use Pivnert. Pivnert will not be on the Regents. So if you're doing PV equals nRT, don't. All right? So, what else can we say about P1, V1, T1? I guess we can kind of talk about the graphs of the relationship between pressure. So this is for a gas. What is the relationship between pressure, volume, and temperature? So, let me rearrange this. If we have pressure, volume, and temperature here, pressure, volume, and temperature here. If pressure remains constant, as volume goes up, this is not how I want to express this at all. So, pressure goes up, volume goes down when temperature is... the reverse is also true. As volume goes up, pressure must be going down. So, pressure and volume have an inverse relationship. The graph for pressure and volume looks like this. So if we're graphing pressure versus volume, as volume is increasing this way, like this is a very high volume, that is a very low pressure. At the beginning, at a very high pressure, we're at a very volume. So as pressure goes up, volume goes down, and vice versa. If pressure stays constant, as volume goes up, temperature goes up. Think of a hot air balloon. So the first one, you want to think of like crushing a can. As you increase pressure on the can, the volume of gas in that can is getting smaller. You're forcing all the gas out. This, you want to think of a hot air balloon. As you heat the hot air balloon, the volume of the balloon goes up. So as temperature goes up, volume is also going up. As temperature goes down, volume is also going down. If volume remains constant, as pressure goes up, temperature goes up. This is when volume remains constant. So, if we have temperature versus pressure, it looks the same as volume versus pressure. Pressure is going up, temperature is also going up. Pressure is going down, temperature is also going down. You can kind of draw a seesaw. So if you have pressure, temperature, and volume, and I'm trying to see if I have a piece of paper here. If you have, because this looks better with a piece of paper, if you have pressure, temperature, and volume, if temperature is constant, as pressure goes up, volume goes down. Do I have a Sharpie? Yeah. That'd be easier to see with this Sharpie. Pressure, temperature, volume. So, if you keep temperature, put your pen or pencil through here. As pressure goes up, volume goes down. As volume goes up, pressure goes down. You put your pencil or pen in the volume slot. As pressure goes up, temperature goes up. As pressure goes down, temperature goes down. Same is true over here. As temperature goes up, volume goes up. Just a little trick. Just a little trick. Any other comments with the ideal gas equation? That you really just kind of have to practice. Take a peek at the review and make sure that I put a lot of Q questions and a lot of P1, V1, T1. So you can not only practice the algebra involved in those equations, but you can also practice making sure you know when to use what equation when. Just take your time. Take your time. Don't make a silly algebra mistake. Earn that point. You need to earn points. You get the highest grade you can. You guys are going to do good. You just got to take your time. Partial pressure. You have a container that has some amount of oxygen in it mixed with some amount of helium. You should be able to figure out the pressure of one of those gases given the total pressure and the pressure of the other gas. So, let's say we knew the total pressure was 10 atmospheres. And we had 3 moles of helium and 4 moles oxygen. What's the partial pressure of each? All right, so we know the total pressure is 10. We need to figure out what's the pressure of the heliums in my container and what's the pressure of my oxygens in my container. So, my total moles is 7. We have 7 moles of gas in the container. So to get the partial pressure of each gas, oxygen and helium, take their given moles over the total moles times the total pressure. So that's oxygen. And then for helium, take the given moles over the total moles and multiply that by the total pressure. So if the container has 7 moles of gas, 4/7 of those moles is oxygen. Therefore, oxygen contributes 4/7 of the pressure. Therefore, helium contributes 3/7 of the pressure. And whatever these answers are, doesn't really matter. This is going to be approximately 40 divided by 7, which is going to be like 5.8. So let's say this is like 5.75 atmospheres. And this is going to be 30 divided by 7, which is going to be even closer, a little bit over 4. Well, based on what I put for the first one, this should be about 4 1/4. I don't know if that's right. I'm just guesstimating, but based on the numbers. So just take the total moles of the container based on the moles given to you of the helium and the oxygen. Express that as a fraction. So oxygen's fraction is 4/7, 4 moles given of oxygen, 7 moles total, that's 4/7. Helium's was 3/7, 3 moles given, 7 moles total. Multiply them each by the total pressure, which was given as 10 atmospheres, and you will get the partial pressure of each. Sometimes it's as easy as they give you the total pressure as 10. If O2's is 8 atmospheres, what's helium's? Sometimes it's as easy as this. They don't even give you these fractions to work with. In which case, if the total pressure is 10, if oxygen's contributing 8 units of that pressure, well, contributing 2 units of that pressure. And I think this is a good spot to end it. Not really seeing any. I'm just looking over my outline here, making sure I didn't miss anything. I'm not seeing anything else that I really want to hit on. I did endo and exothermic, entropy. Let's just do a quick recap. Where did we start? Where did we end? And just if anyone's watching, feel free to send me a question of anything you might have. But this feels good. I think I'm pretty confident I hit everything I want to hit on. Yeah. So today we did a review of the behavior of matter. So this is the more physical changes involved with matter, not chemical changes. So it's everything involving heat and gases. We start off by just defining the few types of energy. So kinetic energy is the energy of motion. So that's involved with changes in temperature. Potential energy is stored energy. So that is involved in phase changes, not changes in temperature. And temperature we defined as the average kinetic energy. So as temperature increases, so does the average kinetic energy. Nothing else matters. If you're asked to calculate the average kinetic energy, see units of liters, milliliters, grams, none of these matter for average kinetic energy, just temperature. Wanted to reintroduce the term of thermal energy because it does pop up often. It is the energy of motion or moving particles, which we can think of as heat. So thermal energy is the energy of motion or moving particles, which we will think of as heat, which we abbreviate using the letter Q. Heat will always transfer energy from higher temperatures to lower temperatures, from a hotter object to a colder object. Heating curves look like this, where you start off as a solid, start to melt, become a liquid, start to vaporize, become a gas. Anywhere in green where these phase changes are occurring, there is no change in temperature. The phases are in this kind of weird mixture of solids and liquids. Think of ice melting. There's some liquid as the ice starts to melt, but it doesn't just instantaneously turns into liquid. Some of it still remains as ice. The parts in red, the kinetic energy is going up because the temperature is going up. The potential energy remains the same. The parts in green, the potential energy is going up because the temperature is not changing. Therefore, that stored energy is changing as we start to melt or vaporize. So the kinetic energy remains the same. Cooling curves are the exact opposite. You just kind of take that heating curve and you flip it around. So gas is at the top now, solid is at the bottom. Well, gas was always at the top. Gas is in the top left, solid is in the bottom right. Remains the same. It's just that now that temperature is going down, the kinetic energy is going down. And when temperature remains constant, kinetic energy remains constant. The potential energy goes down. Endothermic means heat is entering. So, anytime you go through a phase change from solid towards liquid or liquid towards gas, going somewhere trending in that direction up a heating curve, you are endothermic. Exothermic is heat leaving or exiting. And anytime you're going down that cooling curve, you're going from a gas to a solid, you are exothermic. We talked about the Q equations. Those are on your reference table. Entropy is a measure of disorder. As a solid turns into a liquid, which turns into a gas, we have more entropy because they are more disordered. Solid particles are not closer together. They are more ordered. Do not say solids are closer than a liquid. Do not say liquids are closer than a gas. Say solids and liquids are more ordered substances than gases are. So this was like a question where you're comparing the entropy of H2O as a solid versus a liquid. Say the solid is more ordered. Ideal gases was part of the kinetic molecular theory. And this occurs at a high temperature and a low pressure. Ideal gas, ideal, high temp, hot, low pressure. We assume these particles, because this becomes somewhat true, as we approach an ideal gas at these environmental conditions of high temp, low pressure, that they have no volume. They're very, very tiny particles, super tiny, do not attract each other, and because of that no attraction, they move in straight lines. They are moving constantly and randomly, so they don't stop moving, and they're unpredictable. And when they collide elastically, meaning they transfer 100% of their energy from one particle to the other, or if they hit the wall, from one particle to the wall. Avogadro's law. If you're at the same temperature and pressure, which is not the same as STP, but if you're at, usually they say at STP, if you're at the same temperature and pressure, that means if the particles have the same volume, and this is gas only, they have the same volume. So the same volume of particles will have the same number of particles. So 5 liters of carbon dioxide, 5 liters of argon, and 5 liters of helium all have the same exact amount of particles of gas. When you're a gas, pressure goes up. As you increase the pressure, the volume goes down. The graph looks like this. As at a high pressure, there is a low volume. At a high volume, there is a low pressure. They're inversely related. If you now have pressure constant, as volume goes up, temperature goes up. If you now have volume constant, as pressure goes up, temperature goes up. One last thing, and then I want to mention one thing about STP. Oxygens, heliums are in a container. We know the total pressure of the container is 10 atmospheres. If we want to know the individual pressure of each of the gases, add up the total moles, set up a fraction, and multiply. There are 4 moles of oxygen in your container. There are 7 moles total. 4/7 of 10 will give you the amount of pressure oxygen is putting into this system. 3/7 of helium times 10 will give you the pressure of helium. Sometimes it's as simple as, here's the total pressure. If I give you one of these, you should be able to find the other. So if the total is 10, and I tell you helium is 2 atmospheres of that 10, 10 minus 2 is 8. STP, is on table A. So if you see anything about STP in a problem, make sure you come here. They like to throw this in with the P1V1 over T1 equation. They like to have you use STP. Whatever you do, keep your units constant. If the problem gives you atmospheres, stay with atmospheres. If the problem gives you kilopascals, stay with kilopascals. Either way, table A, that rhymed, is STP. STP. Don't use 0 degrees Celsius in the P1, V1, T1 problems because you'll get an answer that doesn't make sense because you'll get 0. That's it. If you have any questions, feel free to text me on Remind or talk to me in class tomorrow.